Okay, guys, May 11th, AP exam is tomorrow. You better know your stuff. Just kidding. So let's go over this. Looking at the integral of 1 over f of x dx is equal to ln of the absolute value of f of x plus c. When is this true? This is true when f of x is a linear function whose leading coefficient is 1. So if this is the integral of 1 over x minus 5 dx, then that would be ln of absolute value x minus 5. If it was the integral of 1 over x plus 14 dx, then that would be the natural log of absolute value x plus 14 plus c. But otherwise, you have to do, like that u substitution or whatever, and you have to make sure that if this is linear, if f of x is linear, then it will look like this times some f prime, right? However, if this was 1 over, let's say f of x is like x squared, right? The integral of 1 over x squared dx is not the natural log of absolute value of x squared plus c, or even 2x times the natural log of absolute value of f of x plus c, which would be x squared, right? This is only true when f of x is linear, and we can go straight from here to there if the slope is 1 or what's in front of the x is just 1. Otherwise, you have to take into account the derivative. Anyway, that's the first
that I want to finish. The error we see is that students.
The next thing that he talks about is if you do have, for improper integrals, the integral from negative infinity to infinity, you have to take the limit as, now he uses a and b here. Remember, I used s and t. S was always my lower limit of integration, and t is always my upper limit of integration. So I would do the limit as s approaches negative infinity of the integral from s to 0 of f of x dx, plus the limit as t approaches infinity of the integral from 0 to t of f of x dx. So you have to evaluate those separately. Okay, so that's another one that he talked about. He goes a little bit into with slope fields, but you're not going to have to draw slope fields for this year. With the, Michael, what are those called again? The little line segments that represent the slopes of all, whatever, it doesn't matter. You're not going to have to draw those because of the format of this year's AP exam. But in solving a separable differential equation, the constant is sometimes omitted, right? So they forget the plus c that goes in that should be there. You have to have that. If you've seen some of the scoring guidelines for some of the past questions on the AP exams, if you don't have the plus c, the maximum you could earn is maybe 2 points out of the 5 or something like that. So you need to have that constant of integration. And then he talks about, and he says it
but they may be asked to solve a separable differential equation, and these two common errors sort of go together, and I'm going to talk about them in the context of a real-world problem.
So he goes through and says, hey, look it, once you integrate both sides, so he says get all your x's and dx's on one side, or y's and dy's on the other side, and integrate both sides. And as soon as you integrate both sides, he also says, this is when I recommend plugging in the initial condition that they're going to give you to solve for the c, right? You could solve for y first, and then after you have solved for y, go through and then plug in your initial condition and solve for c. But I and he, this guy, who's a professor, says, hey, do it now. Do it as soon as you integrate both sides. So that's something that he talks about.
Let's go on and solve for y in terms of x and then use the initial condition, but in my opinion, it's easier to do right here. So there's two things that I do at once.
Anyway.
You cannot use the AST to argue.
He's talking about the alternating series test, right? We talked about that. If a series alternates, that's the -1 to the n or -1 to the n plus 1. Then, so if it alternates, and if the a sub n plus 1 is less than a sub n, meaning that the terms are decreasing in value, the non-alternating parts are decreasing in value, and if the limit as n approaches infinity of a sub n goes to 0, then you know that the series will converge, right? But he says you cannot use.
Sorry, I didn't quite.
Whenever I say series, she thinks I'm talking to her. I'm not. Okay. But you cannot use the alternating series test to talk about divergence. Okay. So he just talks about that. But anyway, then he goes through this saying, show all of your work. But also down in number 6, he says, don't say too much. So there's this, you need to show enough work that is going to get you the points, but you don't want to just write as much as you can, because if even one little thing is incorrect, they got to take points off because what you said is incorrect. So there's this balance of putting down what they're looking for, right? So showing your work, and bald answers are just unsupported answers, answers that don't have anything supporting where that came from, right? So, you know, a good example of this is, obviously this is all calculator, you know, on the calculator part, because they can't see that you're not using a calculator. So if you were to plug something into your calculator, you need to write down what it is that you're typing into your calculator, but the math, the calculus part of that. So don't put in like something that's not in calculus. So back with the other you know, operating system, if you still have an older operating system, it might be fn int of something for the numerical integral. You would never write fn int because that's calculator speak is what that's called, instead of being you know, mathematical language, right? So anyway, show all your work, but don't say too much. Don't write a whole bunch of stuff. He says, do not round intermediate results. Remember, once you get the final answer, you can round to 3 digits to the right of the decimal point. Honestly, if you just left it to 5 or 6 or 7 digits to the right of the decimal point and, you know, boxed your whole answer there, they're not going to mark you wrong. But they allow you to round to 3 digits to the right of the decimal point, round or truncate, I should say. But never do that for something that you're then going to plug into something else. For example, if you're doing an Euler's method problem and you get an answer that's like 3.1592243, plug that whole thing in. Don't say, oh, that's about 3.159, right? You can't do that if you're going to use that information again, meaning if that is just an intermediate answer. If you get to a problem and let's say one of the parts is like really tough. So I'm going to say this a few different times today, but focus on what you know and do as good of a job on the problems that you know. Don't worry or let it get the best of you if you're like, oh no, I don't know this one. See, I knew I should have studied more. I knew it. You can't do that. You look at it and you say, question A, okay, I maybe write down a few different things that you're thinking concept-wise and then move on to B if you don't really know how to do A. Oh, B, oh, this is an Euler's method and I practice that a lot, so I know that one, I'm doing that, right? Oh, C, this is talking about concavity. Oh, I just need to take the derivative and then the second derivative and then, you know, whatever it is, right? Don't give up if you get stuck at any point, right? Don't waste your time erasing the solutions that you figure out are incorrect. A simple X through it or some lines through it, and they're not going to read it, right? And it's not like you're in the test booklet like they normally have, where you have a limited space. If you're doing a problem from the beginning and you're like, oh my God, the whole thing is wrong, crumple it up, later, start a new one, and you could go from there. Make sure you answer the stinking question, right? So they might ask you, where does the function, you know, attain its absolute maximum value? That's the x value. Or what is the absolute maximum value? That's the y value, right? That's f of x value. So answer the question. If it's something like a, related rates, or even, the leaky bathtub problem or whatever it is, always, when you think you're done, go back and say, did I answer the question? Yes, I did. They're asking for the rate at which this, is being done, is leaking out, or whatever it is. Answer the question. Don't simplify a numerical answer. Once you get something, even if it's like 23 over 49, or that's a bad example, like 24 over 48, let's say, whatever, leave it. It doesn't matter. By trying to simplify, you can never earn more points, but you can lose points. So don't worry about simplifying, right? What I've said in class, and I've said this for years, is the only times on an AP exam you really do need to simplify are for the multiple choice portions, because that's how they're going to have it in like A, B, C, D, or E. For their answer choices, they'll be simplified. But for the free response, it doesn't matter. As long as it's mathematically correct, you don't need to simplify. And then set your calculator to radian mode. There you go. So Michael is asking about hey, Olivia, do you have another session right now? Hold on one second. Are you in another dance session right now? Okay, and you were able to get on? Okay, perfect. Sorry, my daughter's doing a Zoom dance thing. So Michael was asking, hey, can we print out what they give us and then take pictures of that and then upload it? You can, and I agree that sometimes with the graphical problems, that might make it easier to work with. If you do have, number one, that does take more time. Number two, you have to have everything set up so you can do that. Not everyone's going to have that. So I would think that they're not going to have problems where you need to do that. So, that's a preference thing, but that's kind of up to you. Dude, my son is kicking butt right now. I got to say something. Evan, great job, dude. Yes. Uh-oh. Good job. He almost ran into a truck right when I said that. Okay. Okay, next. He goes through this guy, Steve Kukoska, who has, again, been a chief grader and has written some of the questions.
You're very good at these, and you'll be able to. You've got a lot of all of you in my class.
The one thing that he said is
thanks, Brian. Tony. A numerical answer, you may lose a point. And this has already been stated here once, don't simplify a numerical answer, especially in this short time frame. Don't waste your time with that. And remember, set your calculator to radian mode. Fantastic. Oh, just one more comment or two more comments here. Look, I thought an awful lot about this in the last couple of weeks about what kind of problems the College Board might be asking on this short exam. And especially where we have technology and open book and open notes, I believe strongly that we're going to get some sort of graphical or tabular problem that you've been practicing. That way, students who have fancy technology, who have sophisticated technology available, will not have an advantage by using an algebraic expression for a function. So I believe very strongly that we're going to see some kind of problem that has a graphical or tabular statement or stem, not algebraic. I also believe very strongly that for BC students, you're going to see something that involves, you're going to see some sort of a question that involves a Taylor series. So to our teachers out there, look.
So that's what he says, is he thinks there's going to be a Taylor series. I think that might be like a part of one of the questions. I don't think that's going to be like a major question. I think that's going to be one part of one question. And for that, again, Evan James, dude, come here. I am so proud of you, buddy. You were rocking it out there. How did you just write it like that, man? Dude, this kid is turning 5 tomorrow. He and his twin sister, they're turning 5 tomorrow. And you're riding a bike like a big boy. Good job, dude. Hey, I love you. Keep up the good work, man. And I like that you have your motorcycle helmet on. That's awesome. Anyway, so what I would do if I were you, for sure, like right now, in fact, get a scratch sheet of paper right now. I'll give you 30 seconds. Get a scratch sheet of paper. Michael, I see that you have your hand up. Was that the question that you typed out? Okay, so let me just remind you about these Taylor series, or the nth degree Taylor polynomials are really what they're going to focus on. So nth degree Taylor polynomials. I'm going to close this window. Okay. So remember, they usually put P sub n, and this is a function of x. So what this means is P for polynomial, n for the nth degree, and it is a function of x. Remember what this is. This is a polynomial. We know what a polynomial is, right? That's something times x plus or minus something to the, and it's in positive integer power. So for something like this, this is going to be, so nth degree Taylor polynomial for f of x centered at x equals c, okay? So this is what we have going on right here. This is going to look like, or did we do A? Did we do centered at x equals A? I forget. Whatever. I'm using C because I have that here now. So this is f of c plus f prime of c over 1 times x minus c to the first power plus f double prime of c over 2 factorial times x minus c to the second power plus, I'm gonna take all of this. Oh no, can I not do that? I think I gotta do it thing by thing. So here we go, I'm gonna make this all a little bit smaller so I can fit more in. Okay, so plus this guy is going to be I think I can do that. F triple prime of c over 3 factorial times x minus c cubed plus dot 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 plus the nth derivative of f evaluated at c over n factorial times x minus c to the nth power. This right here is the formula for the nth degree Taylor polynomial for the function f of x centered at x equals c. This is important, guys. I would write this down. This would be something that I had maybe on its own index card or highlighted on my cheat sheet that I made or whatever else, where I would post it right above my, just so I could see it like on my wall, whatever it is, because I don't want you wasting any time saying, oh, what was that again? What was that? If it's something that both Steve Kokoska and I strongly believe will be at least one part of a question on the AP exam. Have this there for you, okay? Knowing the formula is like the first part, and then applying the formula obviously is the next part, and that's what they're gonna do. Now, they probably will not, for a question like this, they probably wouldn't give you what f of x is algebraically in terms of a function, but they might. But what we've seen in the previous videos that they've posted, on this guy, for those questions dealing with the Taylor series questions, they give you maybe the graph of f, or they give.
I'm so impressed, Tony, because
certain information about. So let's go through. I'm just gonna take a stab. No. Wherever that was. Remember, they gave you, they gave you a table of values of the nth derivative or nth derivatives of h for certain n values, and then gave you another way to find the first derivative, and whatever it is, right? I don't know exactly what part that was that had you use the Taylor polynomial for that one. Oh, so write the third degree Taylor polynomial for h about x equals 0. So this right here is your setup, p sub 3 of x. And you notice that for my class, and like for certain authors like Stewart, who I really like, he uses t, and I use t for Taylor, but they always use p for just polynomial. But anyway, they first have that written out. And then they put, okay, what is h of 0? H of 0 is 3, because that's right there. What is h prime of 0? Oh, that's the slope of the tangent line there. So that's going to be -2. Oh, what's h double prime? Oh, h double prime is 3, but that's over 2 factors. It's just over 2 times x squared. And they have that, so it's not enough that you know the, formula for the Taylor polynomial or nth degree Taylor polynomial, but it's also applying it however it looks, right? So anyway, that's what I would say is important. And then I think I've kind of gone through what I wanted to get through, just with the housekeeping logistical stuff. I want to leave time where you guys could just ask questions, or if you want to see certain things retaught or generality, whatever it is. Let's go. What do you want to see? What do you want me to do? As you're thinking and typing, I don't know if everyone was here when I showed this. These were my kids.
Hi guys, good luck on AP exam tomorrow. Good luck tomorrow. Nothing but 5.
It's pretty rad, pretty awesome. I didn't tell them anything to say either. They just came out with that all by themselves. Okay, that's a complete lie. Okay, logistic growth and decay problems. Yeah, so logistic growth and decay, again, the things that we need to know about logistic growth and decay. Well, let me first give you a quick reminder, and then I'll look for problems. If you have a problem already, like as I'm doing this, let me know, and then we'll go straight to that. But so exponential growth, logistic growth starts looking like exponential growth, but then at some point here, it switches to concave down. And then, so this is a basic graph of your logistic growth curve. And if this right there is, we could call it anything. I'll call it L for the limiting size or the carrying capacity or something like that. This point of inflection which of course is where the concavity changes, is going to occur when the Y value is exactly half of this carrying capacity. So this would be L over 2 or limiting size, right? So that's where that, that occurs. And so we know that for whatever this X value is there, let's call it C, right? So for all X values in between 0 and C, we have that the curve is increasing and concave up. And for all X values greater than C, we have that the curve is going to be increasing and concave down. This is for logistic growth, okay? Logistic decay is just one of these. I'm gonna go into this. So it's gonna look, actually, I think it's only gonna look like this, to be honest with you. Well, I don't wanna do that. Basically, it just, gosh, if the population, that's what I think of for these are like population type problems, because like, let's say it's the number of alligators on this small, island where the population is growing, but you can't continue to grow because there's just not enough resources for all of those alligators to survive. So if you start with the number of alligators, let's say that there's a huge crate of alligators that are dumped onto this thing, and it's more than what the resources can maintain, then you're going to have a decreasing concave up function, and the limit is n approaches infinity is going to be equal to that L value, or that limiting size, or that carrying capacity. So this is the logistic decay. You never see logistic decay on the AP exam. It's going to be logistic growth, if anything. And so this is what it's going to look like. Again, you look at any one of those, logistic, or I should say not logistic, any one of those resources to help guide you, or just to remind you of what we got going on. And we have logistic growth right here for this one. This is what I always go back to, and it gives you certain information about it, about the different, equation. Remember, it starts with dp dt equals k times p times quantity 1 minus p over p sub m. Here they have p sub m instead of L. Sometimes it's C, whatever it is. But if this is the differential equation, then the solution is that carrying capacity divided by 1 minus a to the, a times e to the negative kt. And then you can see that that a value right there is just the initial population minus the carrying capacity divided by initial population again. So that's what that is. So you have this, most students taking the AP Calculus BC exam don't have this readily available. They have to remember it. You have this readily available. So, and then this goes through some of the features of logistic growth. Let's read just very quickly. It says, if the initial population is 0, well, think about that. You start on this island and you start with 0 alligators. What's going to happen? Well, there are no alligators to make more alligators. And so it will always just be 0, right? So nothing's going to happen there. What if the initial number of alligators is equal to this carrying capacity or limiting size? So if I had just this right here, this is if the initial number of whatever it is, you know, for population is exactly equal to the carrying capacity, then it's going to be stable, meaning that you're not going to have an increasing nor decreasing function, or I guess you could say it's both increasing and decreasing, because the by the definition of what it means to be increasing and decreasing, right? Because it's greater than or equal to or less than or equal to. But anyway, so it's just going to be a stable solution. Anyway, so that's the first thing that is the features, and the derivative is just going to be 0. Next, if you have that the initial population is in between 0 and the carrying capacity, then the function's always increasing, and the limit as t approaches infinity goes to the carrying capacity. And the inflection point is when the population is exactly half of the carrying capacity, which is what I said on this thing, right? So this guy's always increasing, the blue curve is always increasing, and so one thing that I should say for both of these, the limit as t approaches infinity of, let's say, f of t equals L, which L is what we're calling our carrying capacity for this graphical example that I have there, right? So there we are, so. Okay, next, what do we got here? If the initial population is greater than the carrying capacity, then the function is always decreasing and concave up. And that's what I have with my red graph right there. Okay? So I guess the question is that enough? Or do you want to look for a problem that deals with logistic growth? Or should I move on to different theorems, mean value theorem versus intermediate value theorem? Who asked for this? Andres and Tyler, logistic growth and decay. Does that answer your question? All right, here we go. With the theorems, okay? So here is very quickly, because you can see, again, you go to any one of those sites, the review sites about you know, the theorems, the intermediate value theorem versus you know, any one of these, right? And they'll talk about, let's see, theorems. Intermediate value theorem. It tells you what the theorem says. Suppose that f of x is continuous on closed interval in a, b, and let m be any number between f of a and f of b, and there exists a number c such that if c is in between a and b, that f of c is equal to m. But then you're like, what the heck does that mean, right? So I'm not going to focus too much necessarily on like you remembering exactly what they say, because you'll have that available. But so this is the IVT, the intermediate value theorem. Let me give you a graphical representation for that. So for any for any function that is continuous on the closed interval from a to b, that's what you need to have, right? If f is continuous on the closed interval from a to b, then so there's got to be some value that's like f of a, right? The function's height at x equals a, and another function's height at f equals b, so we'll call this f of b. Here I happen to have f of b greater than f of a, but f of b could have been, you know, the smaller value. It doesn't matter, and it doesn't have to be in the first quadrant like I have here, but I'm just doing that for simplicity's sake. So here's what this says. if you choose any value in between f of a and f of b, let's say this guy, so they called it m. So if I choose any value in between f of a and f of b, there must be a value in between a and b, call it c, such that f of c is equal to m. So here's what we know. Because f is continuous from a to b, I don't know exactly what this looks like, but I know that there has to be a way that connects f of a and f of b. You're not going to have any like points of discontinuity or, you know, vertical asymptotes or anything like that, right? Because f is continuous on that closed interval. So what it's saying is, no matter what point you choose in between f of a and f of b, we're calling it this guy, you go over, and where this guy hits, right there, that value, that x value, has to be in between a and b. That's what the intermediate value theorem says. Okay? So this is a graphical representation of what the intermediate value theorem says. Now that we have that, let's go back to this. It says, again, suppose that f of x is continuous on the closed interval from a to b. And let m be any number between f of a and f of b. Again, that's like on the y-axis, right? Then there must exist at least one number c. He just says, then there exists a number c. This is from Paul's notes, whatever. I have to sneeze. No, it left me. There must exist at least one number c in between a and b such that f of c is equal to m. So this is graphically what that is saying right there, okay? Now, that's the intermediate value theorem. Here's what the mean value theorem says. Okay, so I have that. Good. Let's move this over here. Move you guys over here. I don't need you anymore, M. Okay, so this is going to be the mean value theorem. So what this says is, if f is continuous, so let me make this, red, okay? So if f is continuous on the closed interval from a to b, and if f is differentiable on the open interval from a to b, then what this says is there must exist at least one point c on the open interval from a to b such that f prime of c equals f of b minus f of a over b minus a. So here's what this says, right? Again, you could look this up and, I don't know, and, Paul's notes, what he has for, this is for continuous. And then he talks about derivatives. So this is going to be after the derivatives. Mean value theorem. So if f of x is continuous on the closed interval and differentiable on the open interval, then there is a number c in between a and b such that f prime of c is equal to this average rate of change. Okay, that's the way that he has it. So here's what it's saying. As long as you don't have any points of discontinuity on the closed interval or any of the things that make it where the derivative doesn't exist at any points of discontinuity, or where there are corners or cusps or vertical tangents, right? If this goes and then there's a vertical tangent and then whatever, the derivative doesn't exist. But anyway, then what this says is, let's draw the average rate of change, which is the slope of the secant line, right? So this guy is f of b minus f of a over b minus a. So what this says is, there has to be at least one value c in between a and b, where f prime of c, which is the slope of the tangent line, is exactly equal to the slope of the secant line. So that's one of the points, or one of the x values, c right there. This looks like it'd be another one right there. So let's call these, I'll call this c sub 1 and c sub 2. So for this example that and there looks like there's another one right there. So let's actually call this c sub 1, c sub 2, and c sub 3. Do you see that though? Who asked for this? Lizzie, do you see that where the slope of the tangent line is equal to the slope of the secant line, right? Okay, now, dude, Evan, you're rocking it, bud. High five. Hey, this is a very important day for my calculus kids. It's a very important day for you too, and I love you. Give me another little bit, and then I'll be out there, and I can't wait to watch you ride, okay? Okay, love you, buddy. So, what types of questions would they ask, right? Where you'd have to use one of these. That's what you guys are asking. Well, first of all, and how would you write it out, right? Okay, so the first thing is the words that would be on the test would say, show that there must exist, you know, or does there must exist, you know, a value in between x equals 2 and x equals 5, where f prime is equal to this, is equal to 7. And you say, well, the secant line, the average rate of change is 7, and I have a, let's say, continuous function, and it's differentiable on the open interval. So based on that, the mean value theorem would hold true. And you would say, because f of x is continuous on the closed interval from 2 to 5 and differentiable on the open interval from 2 to 5, then there must exist at least one value c on the open interval from 2 to 5 such that f prime of c is equal to f of b minus f a over b minus a. So that'd be f of 5 minus f of 2 over 5 minus 2, which is equal to 7, because that, you'd have to say that as well. And, you know, use it that way. There was a question on one of those reviews, I think on number 30 or 31, video 30 or 31. You know, I could go back to that if you really want to see it, where the mean value theorem was used. The intermediate value theorem, again, right, only deals with, has nothing to do with differentiability. It's only with continuity. So as long as you know f is continuous, so sometimes it'll say, her velocity, Jenna's velocity at T1 is -3. Her velocity at T2 is +5. Does there have to be a point in between T1 and T2 where her velocity is equal to 0? So oftentimes it's crossing over that, you know, x-axis or t-axis or whatever that happens to be. And so you would say by the intermediate value theorem, yes, there must exist, you know. Now, in all honesty, and I don't know why I'm whispering right here, most of the time on the AP exam where they ask you a question about the mean value theorem or intermediate value theorem, the answer is yes, it must, because of the intermediate value theorem or mean value theorem. Meaning if they say, does there must exist a time when this happens? Most of the time the answer is yes, by one of these theorems, okay? Okay, if you want to see more on that, I'll go through one of those, you know, whatever video number that was. Maybe one of you guys could look it up for me if you want to see more on that, to talk about how to use that. Next, we have improper integral review. Okay, improper integral. What are improper integrals again? Well, it started out with those problems that I said, like the integral from -1 to 3 of 1 over x dx, right? So when we first, saw this problem, we said, oh, this is just, okay, what's the antiderivative of 1 over x? Oh, that's ln of absolute value x going from -1 to 3. Okay, so this is equal to ln of absolute value 3 minus ln of absolute value -1. So this is going to be ln of 3 minus, so absolute value of -1 is +1, ln of 1 is 0, so it's just going to be ln of 3. Yeah? And then we said, no. Do you remember that? And I said, until we first talked about improper integrals, we said, can't do this yet. Do you remember us going through that whole thing? Well, and then I said, wait a second, we can do this now. If we, so this was before, right? This was before was this. So that was not correct. That ln of 3 is not correct. And it's not correct because the integrand is not continuous on the entire interval from -1 to 3, right? Namely, it's not even defined when x is equal to 0. So anyway, so then what we did is we took this problem and we said, okay, so we have to think about this as, so now we say the integral from -1 to 3 of 1 over x dx is really equal to the integral from -1 to 0 of 1 over x dx plus the integral from 0 to 3 of 1 over x dx. And then we said, hey, let's look at this. This guy, which is the same as this guy, I broke it up from -1 to 0 and 0 to 3 because at x equals 0, the integrand is not even defined. So I would say that this is equal to the limit as t approaches 0 from which way? From the left or right?
Left.
Left. And why is it from the left? Because on the, if you look at -1 to 0, you're approaching 0 from the left on this interval, right? Plus the limit as s approaches 0 from the right of the integral from s to 3 of 1 over x dx, because on this interval we have from 0 to 3, so I would be approaching 0 from the right on that guy, okay? And then you look at any one of these, and then you take this, let's just say we focus on this guy right there, and we would say, okay, well, this guy ends up being the limit as t approaches 0 from the left of ln of x, absolute value of x, going from -1 to t. Which is equal to the limit as t approaches 0 from the left of ln of absolute value t minus ln of absolute value -1, which is limit as t approaches 0. Well, actually, I guess we could just plug it in as of this point, right? This guy ends up being 0, right? Because -1, the absolute value is just 1, and ln of 1 is 0. But what about this guy? What do we have if we plug in something that is getting very close to 0, but because I have absolute value marks in there, that's going to make it so it's very small, meaning very close to 0, but always positive, even though I'm approaching 0 from the left, like -0.1, -0.001, whatever. I put in absolute value marks, that makes it positive. So what does ln of something approaching 0 but getting very close to 0 and always positive, what does that go to? Well, that's like I'm going there. This guy goes to -infinity. So this goes to -infinity, therefore does not exist. So that tells me that's part of this guy, as long as any part goes to one of the infinities, we say, therefore, this guy diverges. You don't need the exclamation point. Right? That guy diverges. That's what we've shown there. So this is one of the types of forms of improper integrals. The other ones that are easier to identify are where the limits are either one of the or both of the infinities. So another one might be, hey, let's look at, so another example might be the integral from 1 to infinity of 1 over t squared dt. Okay, something like this. So for this, you'd say, okay, like we talked about before, the integral of 1 over t squared is not ln of absolute value of t squared. And it's not even, so anyway, what we would have to do is I'd say, okay, first of all, this is equal to the limit as t approaches infinity of the integral from 1 to t. Sorry, do you see what I'm doing here? I need to choose a different variable or letter because t is already used. So now I would say, oops, I used t there. I can't use t because t is what this variable is. So let's use a, okay? This is t to the negative second dt. So this is the limit as a approaches infinity of, what's the antiderivative of t to the negative second? Somebody speak to me.
Negative t to the negative 1.
Good. And that's going from 1 to a. So this ends up being, let me bring that down here, the limit as a approaches infinity of, so that's going to give me negative 1 over a minus negative 1 over 1. Well, that's plus a positive, right? Slash and slash. So now when I plug in that limit as a approaches infinity, this goes to 0, right? And so this whole thing just goes to 1. And so that is my answer. So if I take, 1 over t squared, and I take the integral from 1 to infinity of that thing with respect to t, that's just going to be 1. Okay? So that's the basics or a quick review on improper integrals. Anything else I can do for you? Kayla asked for related rates review. Okay. Related rates is an application of implicit differentiation. Okay. So related rates, let me just write that down. Related rates is an application of implicit differentiation. Okay, so this is when they'll say, let me just pull one up really quickly and then I could talk about it. I'm just gonna, I don't even know. I'm just gonna grab one of these guys. Okay, here we go. plane I'll put this over here. Okay. So there are three main types of related rates problems. Okay. That I, and again, this is just me. I classify them into three different types. Those three types are your basic Pythagorean theorem, the second is other geometry. So that's maybe like, you know, there's a gravel pit and the gravel is such the size that as it's coming up, it forms a cone. And is the rate that the gravel was being you know, deposited on the top of this pile, and then the cone is growing, and so the radius is growing and the height is growing and whatever, right? So it's another geometric. Or there's a snowball that is going down, and it's a perfect sphere, of course, and it's going down and it's increasing in size as it's going down, you know, whatever. Or the third type are those shadow problems, right? So shadow. So with the shadow problems, it's, you know, you got to look at, there's the rate that the person is walking plus the rate that the shadow is growing from his or her body. And so you have that stuff. Anyway, let's look at this guy, a plane flying directly away from you at 500 miles per hour at an altitude of 3 miles. How fast is the plane's distance from you increasing at the moment when the plane is flying over a point on the ground that is exactly 4 miles from you? Okay, so this is a basic you know, problem. This right here is constant at 3 miles. The plane is flying at exactly an altitude of exactly 3 miles. It's not dipping down or going up or anything like that. It's at a constant altitude. Now, what some people want to do is they say, okay, oh, it's 4 miles from me. So let's say that I'm right here. Okay, let's put you right here. That's where I am. So this must be 4. And they put 4 in. You cannot plug in anything for the other variables that are changing until after you differentiate. Okay? So that's the main thing there is you have to keep the variables. So you have to, first of all, introduce variables, understand the problem, introduce variables, and then when you implicitly differentiate, after you differentiate, then you can introduce what they give you in terms of the other values, like 4 miles and all that stuff. So just looking at this, what I would say is, okay, x squared plus 3 squared equals, they call this y. I always call the vertical y and then the slant z. It just makes more sense to me, but whatever. They call this y, so I'm going to call that y over there. So then I would differentiate with respect to time to get 2x dx dt equals 2y dy dt. Okay. So now you could divide both sides by 2 and you would get this. Okay, so now this is when you could plug in the other information that they give you. So what's my unknown? Well, that's the rate that the distance from the person to the plane is changing. That is known as dy dt, the rate that y is changing with respect to time. Okay. So let's look at this. They say a plane is flying directly away from you at 500 miles per hour. So, okay, that would be dx dt, the rate that x is changing. So dx dt equals 500 miles per hour. Now the question is, every time I plug in a value that for a rate, I ask myself, should that be positive or should it be negative? So we look at dx dt. I am calling this thing x, the distance from me to the point directly under the plane. Is x increasing or decreasing at this moment? Well, x is increasing, right? If x is increasing, dx dt must be positive. Go through that every single time you're doing one of these implicit differentiation or related rates types of problems to verify that that rate is positive. If that plane happened to be flying the other way, then x would be decreasing and dx dt would be negative. But in this case, it says a plane is flying away from us, so therefore dx dt is going to be positive. Okay? Now, we also are given that the plane is exactly, or the point under the plane away from us is 4 miles, right? Because when the plane is flying over a point on the ground 4 miles from you, so x is 4. So just with that, I have that this is 4 miles, right? This x is 4. The dx dt is 500 miles per hour is equal to y. I don't have y, but guess what? We have a right triangle there. We know that the height is 3 and that base is 4. So based on the Pythagorean triple, we know that that must be a 3, 4, 5. So this must be 5 miles right there, right? It's a 3, 4, 5 right triangle. So this is equal to 5 miles times dy dt. Well, now everything is there except for the unknown rate that I'm looking for, which is dy dt. So I divide both sides by 5 miles, and that allows me to solve for dy dt. Dy dt is equal to 500 divided by 5 is 100. Miles, those cancel out. I'm left with 400 miles per hour. Okay, so that's an example of one of the related rates problems. They're probably, now let's be honest, right? Let's think about this logically. If I were writing this AP exam, I would want to test that you understand related rates. If related rates is one of the concepts that I'm testing, I want to make sure that you understand related rates. I don't want it to take up all of your time. So they're going to have to give you a lot of information or make it a simpler problem like this, which is just a right triangle, simple Pythagorean theorem problem. You know, instead of giving you something that's going to be ridiculously complicated. Okay, so there you go. I think that's good for related rates. Dude, my little guy is rocking it. He'd only ridden a bike like just with me lifting up my hands and him riding, and then like he'd say, "Oh, help!" and then I'd go. But now he's like, he's rocking it, dude. It's amazing. I gotta show you. Oh, I can't. I got all these cables. Anyway, what else? It's 4:23. I initially said maybe like 4:30 or something like that, but if you need a little bit more, we'll do that. If they give you a cone related rates problem, honestly, I think what you should do is, you know, look up volume of a cone. It's not going to be that tough. A volume of a cone. Look at, this is what you got. You ready? We have this cone there. And this is the radius. And that's the height. And you know that the volume, or even if you don't know, you can look it up really quickly, is equal to pi thirds r squared h. They'll give you a way to relate r's and h's probably. And they'll say, this is the rate that volume is increasing. It won't be that bad. And what if the height is always twice the radius? So then, oh, h equals 2r. And then you change h for 2r. So it won't be that bad, right? You got it. Anyway. Keaton asked for the washer method. Okay, cool. So for the washer method, well, everything in terms of So I will go over a washer method, but let me just give you a quick review over, so let's say that if this is my function, and I am saying function, but this doesn't have, we don't have to have functions, but this is what we dealt with, right? So remember, it's up to you how you want your top minus bottoms to run. That is the first thing that you think about for any area or volume problem. How do I want my top minus bottoms to run? Up and down, perpendicular to the x-axis, which means that everything is in terms of x, or perpendicular to the y-axis, in which case everything is in terms of y. For this one, everything would be in terms of the, or perpendicular to the x-axis, right? So now let's say that I want to rotate this about the line. Let's make it y equals c, okay? And let's say that line lies below the region, okay? So if I have this, think about it. If you take any one of these guys and you rotate it around that line y equals c, it's gonna look like a washer, right? So if you take your super sharp samurai sword and you slice it, that thing is gonna look like a washer. So it's gonna look like this. So this is the point C that you're rotating it about, and this would be your big radius, and that's your little radius, right? And so this is the way that I always set it up. I said, okay, this is a washer method problem. I know that the area is equal to pi times quantity, big R squared minus little r squared. So what is big R? What is little r? So here we go. For this problem, how you start with these is you say, well, first of all, you know everything's in terms of x's because the top minus bottom lies perpendicular or runs perpendicular to the x-axis, so everything is in terms of x's. But what is big R? So what's bigger, the region or the line? The region is. So you go to the uppermost function, so f of x minus whatever this is, c. That's your big R. What's your little r? The guy that's closest to the line that you're writing about minus that guy. So in this case, it's g of x minus c. And so your area function in terms of x is pi times, I'm going to move this whole thing over a little bit. Big R squared, f of x minus c squared minus little r squared, g of x minus c squared. Okay, and then the volume is always equal to the integral from a to b of your area, d whatever. This could be dx or dy, right? So in this case, this is a of x dx. So that's what that would look like. You guys are talking about no AP exams. I don't know what you're talking about. Okay, so there you go. Now, let's say, what if, Keaton, what if this y equals c was up here? Let me ask you, what would change? Well, everything is still in terms of x, right? Our top minus bottom still run perpendicular to the x-axis, so everything's in terms of x. But now when you ask yourself, what's bigger, the region or the line it's being rotated about? The line is. So in this case, your big R would be the line minus the guy that's furthest away. And your little r is going to be the line minus the guy that's closest. Does that make sense, Keaton? Okay, so let's talk about shell. So this has been washer. Remember, how do you determine if it's the washer or shell again? Okay, if your top minus bottoms, so first of all, top minus bottoms running perpendicular to the x-axis, everything is in terms of x's, no matter what method you use. Top minus bottoms running perpendicular to the y-axis, everything is in terms of y, no matter what method you use. Then you say, okay, how are my top minus bottoms running with respect to the line I'm rotating about? For these problems, top minus bottom are running perpendicular, so it was washer. If our line that we're rotating about is, get down here. Come on. Okay, so if my top minus bottom, let's say is, not top minus bottom, if the line I'm rotating about is over here, now let's talk about this, okay? So let's get rid of this because that's no longer valid for this problem. So here we go. What if my top, what if the line I'm rotating about is over there? And let's call this x equals d. Gosh, you know, like, I gotta make this pink. Okay, so that's really a purpley, whatever. Okay, so I'm rotating about this. So now, remember, because your top minus bottoms run parallel to the line that you're rotating about, you're gonna have a shell, and really it's a cylinder. It's the shell of a cylinder, or the lateral area of a cylinder. So cylindrical shell, we start with the area is equal to 2 pi r times h. 2 pi r h. 2 pi r is the circumference times the height. Because remember with the water bottle label that I unraveled, and so it looked just like a rectangle, and I said the length of this, or base of that, is really 2 pi times the radius, or the circumference of that circle, and the height, h, is just the height of that thing. So that's where that comes from. So then you ask yourself, what is r and what is h? Well, h is just going to be, that's the easiest guy. That's just your top minus bottom. So in this case, it's f of x minus g of x. And then r, this is when you have to say, okay, the whole region is assigned x or y, you know, depending on how your top minus bottoms are running. In this case, they're running perpendicular to the x-axis, so everything is in terms of x. So the region is x. Ask yourself now, what's larger? The region, or what's bigger, the region or the line it's being rotated about? Well, here I happen to have x equals d to the left, meaning that those are smaller values than the region. So the region is bigger. So that gets assigned x. So it's going to be x minus d. Okay? And then you would say, okay, this is my area function, a of x equals 2 pi times my radius times my height. And then the volume is always just the integral from a to b of your area. In this case, it's going to look like that. Okay. Now, what would change if this region, not the region, if the line that I'm rotating it about is over here? What changes? Well, I'm still using the shell method because my top minus bottoms are still parallel to the line I'm rotating about. So it's still going to be the shell method. My h is still f of x minus g of x, right? Top minus bottom, or blue minus red in this case. But now my r, right? My r is going to change. So let's do that. When I ask myself what's bigger, the region or the line I'm rotating about, the line happens to be to the right of the region. So the line is bigger. So this is going to look like d minus x. for my R. So then up here, instead of x minus d, it's just going to be d minus x. Shell method, okay? So what do we think? What are we thinking here? You guys ready for this? It's such a different world, man. I usually get my energy and direction and like, you know, what you want to see, you know, how I'm going to tailor my lessons and my reviews to you guys. But my interaction is definitely significantly less. I feel like most of you, and I don't blame you, I would be the same person where I would go on and I would probably not ever, you know, say anything or type anything, and I'd just be like watching and like, you know, doing the work and, you know, but, and only if I had like a you know, question that I really needed, I would ask and stuff. But it's tougher for me. I can't see your faces. I can't see what you know, what you don't know. If you guys are like, okay, yeah, that makes sense. Or like, I'm doing a problem and you're like what, you know what I mean? That I typically see in class. So it's tough, but you know, I think the main thing is there are so many resources out there. Don't get overwhelmed by all the resources, but just know that they are there if you want to, you know, do a major cram session right now. I think those videos like I put on my Google Classroom that I've mentioned quite a few times, they are very valuable, right? And definitely I would start with, you might want to do Taylor, I don't know, how about Taylor polynomial approximations? That would be good, number 12, but if you need that, but really the review stuff, the review, and so this starts on integration techniques review and you know, free response question practice. So really from video 15 on, I would you know, look at what I needed help with. I would also, like I said initially, get my stuff ready. You know, have it so I'm all prepared. Make sure I have my ID number, your AP ID number. Have your pages all ready. Keep practicing that upload process until you get it down so you can, you know, okay, I can get this done in 3 minutes, or I can get this, it takes me like 4 minutes or whatever, so that you don't go over your time. Set timers, do the things that you have to do to make sure that you got it going on, and, you know, print out if you want to, or have just, you know, different sites up, or different, maybe on your iPad or tablet, whatever, different things that you want to access. You know, my website is decent in terms of, you know, going through the, all, you know, quick review of everything all the way through. But, and then, like I said, the main thing is focus on what you know, and just think about it not as, oh, I might get a point off here, I might get a point off there, but again, you're thinking about it as, how can I get the most points? You're gobbling up points. It's not like, oh, I missed that one, I missed that one. It's how many points can I get, right? Like a positive mindset of keep collecting, accumulating those points, instead of like, oh, that one, oh, I know I didn't get that one, because that's usually what students focus on. You can't. It's all about just getting as many points as you can. And like I said, go through maybe the last couple of videos on recommendations and little tips and tricks and all that. but I think I've covered them in my sessions. So never found anything about tabs. Another question about that. Never once found anything about limiting the number of tabs. Heck, I would be destroyed with all my tabs open. But yeah, I've never once found anything about number of tabs open. So I think, you're good there. Maybe for you guys who took the AP Gov test, was there anything that stated anything about number of tabs, or you probably didn't need a bunch of tabs open, or?
No, there wasn't anything. And I think there was like a YouTube video talking about like the rules or something. And then they said you could Google stuff, but not collaborate. So I can't imagine they'd be watching your tabs
Yeah,
that closely to letting you Google.
cool.
There was like a rumor going around that they're gonna be like, they're gonna be like spying through microphones and like the webcam on your computer and stuff.
Yeah.
I don't know how true it is, but that's
Well,
what
I
heard.
would. Was that Sean talking? Sean, I
Yeah, that was me.
would make a hat out of tinfoil and just wear that the whole time, and then you'll be good.
I don't even have a camera, so like, it wouldn't make a difference. But that's what I heard.
Got it. Yeah, I would still, if I were you, I would make your tinfoil hat. I think that'd be good. So they can't, get your brain waves.
Of course.
Yeah, I haven't heard anything like that either. I think you're good. It's just focus on, what we've been doing all year long. I think if you've been here with us going through, I think we've kind of hit as much as we can. I think, like I said, they're going to give you something that's either a graph, table of values, something like that. We've hit so many free response questions that deal with problems like that. I think accumulation of change, which is the where you are equals where you were plus how much you've changed. I think that's going to be in there at least somewhere for sure. I would say maybe like the leaky bathtub, where something's coming in, something's leaving, and something like a Taylor polynomial. I think those are all concepts that I would especially prepare for. They're also going to have other stuff, but the thing is, there are so many concepts that I don't want to say I'd also focus on this, because for me, just as likely it would be any one of the other guys. So, but I would focus on the stuff that we've been talking about. All right, guys. Don't cram so much that you don't get enough sleep tonight. You know how much sleep you need in order to function well the next day. Don't sleep in past 10:30 or even past 10 o'clock. Make sure that you get up. What I always do, and everyone's different, but what I always do is when I have something that's important, I make sure that I wake up just a little bit earlier than I normally do. I eat well and shower and do whatever, and like make sure I'm dressed for the day. If you've been one of those people in quarantine that's like always like just lounging in your pajamas or doing whatever, I'm not saying get like dressed up in a suit or anything, but like at least get dressed. For me, I've always seen like a collared shirt or like a button down or something like that. For me, just like I look at myself in the mirror, or I look down and I see it, and it just reminds me, oh yeah, I got to be on top of my stuff today. I need my A game. And so if that's something that that might help you, whatever, but that's just something that I always do. And again, show them what you know. You know what I mean? I think they're going to be, I don't want to say more lenient or forgiving or anything like that, but I got to think that they understand the situation that, the students are in. And I think you guys have a good foundation. It's just you going and showing them what you know, right? This is something that when you take an AP exam in anything, it's important. I genuinely feel, and maybe I am biased, but AP Calculus is one of those tests that, you know, by even taking this AP exam and by passing the AP exam, it just sets you on another level. And, you know, I think you guys have already shown that you are, you know, resilient and just amazing for everything that you've had to endure this year. And now it's time for you to just show, right? Show them. Leave everything out there. Just make sure that you're doing everything you possibly can that is going to show them what you know. And I think you're going to do great. You know, still study. I think you guys, you know, if you have each other's numbers and text each other, or even email each other, or do whatever you got to do. You know, I think it's great having that support system. If you have any last minute little questions, you can always email me. But other than that, go get them, man. Go get them. And for the rest of this week, so we usually meet on Tuesdays and Thursdays. I would like to meet on Thursday at our normal time. What time is that again? 10:30, right? So Thursday at 10:30, just kind of get your feedback on how you felt it was. Or if you even want to email me or private, you know, message me in Google Classroom or something. And I'm not saying, Mr. Grolu, this was the type of, I'm not asking for what's on the test, right? At all. What I'm saying is reaction. Like, I felt okay. I felt like the questions were fair. Stuff like that. That's what, you know, again, those are the little things that I look forward to that obviously we're all missing out on a little bit, but maybe shoot me a little something like that. All right. All right, guys. Best of luck tomorrow. I don't even want to say luck. I want to say skill. Like, go get them. You got this.
Do amazing! I believe in you.
What she said.
Tell them. Say, go get those fives. Go tell them. Go tell them straight.
Yeah, Olivia, come here. Say, go get those fives. Come here.
Tell the TV.
That's a score.
Hold on.
What is it?
Right there. Go get those fives.
Go get those fives.
That's right. Go get those fives.
Ow, you're tickling me.
I'm sorry, I'm tickling you. The time on Thursday, some of you guys, that's right, you guys are taking other AP exams. You know, if you can't make it at that time, what class is that, Michael, for the other AP exam? That's for Chem. Are a lot of you guys taking the AP Chem? Just two of you guys, okay. So I'm gonna keep that time, but if you can't make it, just maybe shoot me an email or a you know, message on Google Classroom, and we'll go from there. All right. All right, guys.
Good luck.
Go get them. Good luck. Show them what you know.
Get those two problems.
I know. Only two problems, but you guys got this. All right. Go get him. Get to studying, man. What are you doing on here? You got to study for your AP exam tomorrow. All right. See you guys on Thursday. Good luck. Bye, guys.
Now, he's so excited.
Hi, Growler.
Bye, guys. Go get him. This is one of my students. Evan, dude. I can't wait to see, dude.
Also, Avery does not trust mommy. She only wants that.
For what, Mama?
She took the training wheels off the shark bike.
Yeah. And now we're gonna hook the training wheel on to the other bike, the fire bike.